Why don't you notice the hole in your vision that exists in each eye? Right now, somewhere in your visual field, there is a tiny region where the world literally disappears, yet you keep reading, walking, and scrolling as if nothing is missing. That everyday mystery, the unnoticed blind spot, tells us something profound about how perception works. Your brain is not a camera recording reality. It is an active builder that fills gaps, predicts what should be there, and sometimes cheats in the most elegant way. In this video, we'll take a guided tour from the anatomy of the eye to the algorithms of the cortex. We'll do simple experiments you can try, and we will reach a clean, practical insight. The reason you don't notice the blind spot reveals the brain's core strategy for making sense of an uncertain world. Let's begin with the anatomy because the blind spot is a physical fact. At the back of each eye, where all the nerve fibers exit to form the optic nerve, there is a small patch with no photoreceptors. No rods, no cones, nothing to detect light. That patch is the optic disc, and it creates an absolute scotoma, a tiny gap in the raw input. If you cover one eye and look straight ahead, you can make a small dot vanish right in front of you. The disappearance is dramatic when you know where to look, but under normal viewing, you never sense any hole. Why? The short answer is that the visual system fills in the missing information using surrounding patterns and prior knowledge. But to make that intuitive, we need an analogy. Imagine you're reading a long, well-known sentence printed on a strip of paper that you slowly slide past a small window. In the window, a tiny letter-sized patch is missing. If the missing patch isolates a single letter, you may notice the gap. But if the missing patch slices through a predictable pattern, say a repeated word or a solid color, your mind will effortlessly reconstruct the missing piece and you won't notice. The brain treats the blind spot like that small, predictable hole. It reconstructs the likely content based on the context to preserve continuity. Now let's walk the path from the eye to perception. The retina encodes light and sends signals through the optic nerve to the lateral geniculate nucleus, LGN, and then to primary visual cortex, V1. V1 contains a map of the visual field, including the area corresponding to the optic disc. Neurons around that cortical patch are sensitive to edges, textures, orientation, and motion. When input is missing from the blind spot, nearby neurons still respond to the borders and the surrounding patterns. Through a combination of lateral connections and higher-level feedback, the cortex essentially paints plausible continuations into the blank region. Two mechanisms are especially important. First, local interpolation. Neurons detect the orientation of edges on either side of the blind spot and extend those edges inward. If a straight line crosses the blind spot, the brain extends that line through the empty patch so you perceive a continuous line. Second, predictive filling via feedback. Higher visual areas, which represent larger, more abstract features and object knowledge, send expectations down to V1. If your brain expects a uniformly colored surface or a familiar object, it biases the reconstruction accordingly. These processes are not mystical. They are implementable in computation. Modern machine vision uses very similar tricks. When data is missing or corrupted, algorithms inpaint the image by matching surrounding textures and by relying on learned priors about objects. The human brain does the same, but in real time and with low energy cost. To make this concrete, try a simple demonstration. Close your left eye and focus your right eye on a small cross drawn on a sheet of paper. Hold the paper about 40 centimeters away. Place a dot to the right of the cross and slowly move the sheet while keeping your gaze fixed on the cross. At a certain position, the dot will vanish. This vanishing marks the location of your blind spot. Now examine the gap. Do you see a hole, or do you see the background pattern continuing through the missing dot? Most viewers report that the background fills in smoothly. That subjective continuity is the brain's handiwork. But filling in has limits and interesting side effects. When the region around the blind spot is highly unpredictable, full of varied textures or complex objects, filling in can produce visible artifacts or uncertainty. Scientists exploit these limits to study the brain's reconstruction algorithms. One famous phenomenon is perceptual completion, where the brain perceives a partially hidden object as whole. If a circle is partly occluded by a rectangle, you still see a full circle behind the rectangle. That's amidal completion. The brain infers the hidden parts. The blind spot uses similar logic, but without an actual occluder. Instead, missing input is treated like hidden content, and the brain guesses what belongs there. Modern neuroscience frames these effects in predictive coding terms. The brain is constantly generating predictions about sensory input and updating them with incoming signals. When input is missing, prediction dominates. In the blind spot, The visual system's best guess becomes perception. This explains why the blind spot is often more noticeable when you force your brain to rely on raw sensory data. For example, with stabilized images. Stabilized images are fixed on the retina so tiny eye movements can't refresh the pattern. Under those conditions, small regions fade and disappear, a phenomenon called Troxler fading, and any hole becomes more evident. That tells us the system uses both predictions and continuous sampling via microsaccades to maintain stable perception. Speaking of eye movements, saccades play another crucial role. Our eyes make rapid jumps 3 to 4 times per second, and during those jumps, perception is suppressed to avoid blurring. The brain stitches together pre- and post-saccadic snapshots, effectively hiding gaps and smoothing transitions. The blind spot is thus masked by both prediction and motion. But don't mistake filling in for perfect reconstruction. In pathological cases like scotomas caused by retinal detachment or stroke, the brain initially notices the hole. Over time, many patients report that the missing region becomes less obvious as perceptual filling in adapts. This adaptive filling in is useful, but can also hide clinically significant loss. That is why objective testing like perimetry matters in medicine. The capacity to hide deficits is elegant but dangerous when you assume intact vision. There are other intriguing illusions that reveal the brain's preference for stability and continuity. Change blindness experiments show we miss large changes when they coincide with a saccade or a transient interruption. The brain prioritizes narrative coherence over pixel-perfect accuracy. Similarly, in the famous invisible gorilla experiment, subjects focused on a counting task failed to see a gorilla walking through the scene. The lesson is consistent. Attention and expectation shape perception far more than raw sensory detail. Let's return to the blind spot and explore some creative experiments and practical takeaways. You can map both blind spots and study filling in by using simple tools. 2 dots on paper, a fixation cross, and 1 covered eye. Try varying the complexity of the background. Use a uniform gray field, a striped pattern, and a photograph full of detail. Notice how the blind spot disappears more seamlessly on uniform or smoothly varying backgrounds and becomes more conspicuous on high-frequency textures. This is a live demonstration of how context constrains prediction. For photographers and designers, this is useful. Background continuity helps hide small defects, while complex textures draw attention. For interface designers, avoid placing important elements where the viewer's eyes often fixate in a way that could mask them. For clinicians, remember that subjective experience can underreport functional loss, so objective measurement is essential. Finally, we arrive at the neat conceptual punchline. The blind spot is not a bug in perception. It is a window into the brain's operating system. It shows that perception is inference. The brain trades exactness for coherence and speed. It uses local interpolation, global prediction, and active sampling to turn patchy inputs into a stable, continuous world. That strategy is efficient, robust, and adaptive, but it also lets the mind hide its own mistakes. When you next look at a smooth horizon or a seamless photograph, remember that part of what you see was painted by expectation. The world you perceive is half given by light and half constructed by the brain. If this short voyage into your unseen blind spot made you look at perception differently, you've just experienced the same doubling. A small shift in observation changes the whole story. Try the blind spot demo, try Troxler fading, and notice where your brain fills in. If you enjoyed this kind of experiment and want more videos that turn everyday magic into science, press like. Share this with someone curious about how seeing really works, and subscribe to How It Actually Works. Here we give you the keys to hidden mechanics, so the next time the world feels seamless, you'll know a little of the clever machinery that keeps it that way.